Hello, my name is Jeff Delmerico. I'm a research scientist at the Mixed Reality and AI Lab in Zurich, Switzerland, part of Microsoft Mixed Reality. And on behalf of my colleague Helen Oleynikova, I'd like to welcome you to our webinar entitled Mixed Reality and Robotics, Unlocking More Intuitive Human-Machine Collaboration. So before we get started, I'd like to introduce some of the concepts and terminology that we'll refer to during this presentation. So first, we should define what is mixed reality. So mixed reality exists on a spectrum between the digital and physical worlds. Virtual reality on one end is a fully artificial environment where you're immersed in purely virtual content. Augmented reality visualizes virtual objects overlaid on the real world and gives the user an opportunity to see the real world enhanced with this digital world. Mixed reality sits in the middle and offers the opportunity for an immersive experience where the user can both visualize and interact with the digital world through a mixed reality device. And so this takes the form of currently many different types of handheld mobile devices, such as AR-capable phones and tablets, and also VR headsets and mixed reality devices like the Microsoft HoloLens. And so these all we consider having some capabilities that fall into mixed reality devices. We're also interested in talking about robots, and these also take many forms, from industrial robots that perform manufacturing to logistic robots that move things around in a warehouse, to ground-based and also aerial inspection robots and service robots and so on. So these take a really wide variety of forms. We're today going to be talking mostly about interacting with mobile ground robots. But many of the principles that we talk about here are applicable to a broad class of robot devices. And we want to bring these mobile, these robots and mixed reality devices together in our vision of the workplace of the future in which humans and robots can work together and collaborate in an intuitive way with one another, allowing human capabilities and robot capabilities to complement one another. And one of the key functions here is that the humans and the robots need to share an understanding of the space that they occupy and operate in. And so that's one of the major themes of today's webinar is colocalization. The other one is interaction. And so this is a quick video showing one type of interaction that we want to enable with mixed reality, which is gesture control. So the first half of this webinar will focus on human-robot interaction. And then I'll turn it over to my colleague Helen for the other half on colocalization. So the current popular interaction paradigm for controlling robots typically involves sitting behind a normal desktop computer or laptop using a keyboard and mouse. The operator and the robot aren't necessarily sharing the same space, and any spatial information that the user wants to communicate to the robot or the robot needs to communicate to the user has to be translated from the robot's frame of reference to the user's. One of the other things that is challenging in this paradigm is that the user can't easily see the robot's intentions. So some of our goals for mixed reality-based human-robot interaction is to enable this natural mode of interaction and cooperation. And because we can use mixed reality to visualize things from the robot's reference frame, we're able to demonstrate to show the robot's intentions and improve safety and transparency for what the robot is doing. And we also want to be able to enable new applications and research avenues that come out of these different ways of working with robots. And so in this talk, we'll talk a little bit about the current technology that exists and some of the tools for developing in this space, as well as spatial data representations in mixed reality, and also based on the capabilities of your mixed reality device, different modes of interaction in mixed reality. So to start, when we talk about mixed reality devices, as I said, the devices exist on sort of a continuum, and these devices interact with, to different degrees, the physical world and the digital world. And so when we think about augmented reality, we have some of the AR-capable mobile devices that use Android or iOS and their AR libraries to generate and visualize AR content. Sort of at the other fully digital end of the spectrum, we have some virtual reality devices that allow you to have an immersive VR experience. And there are also quite a few mixed reality headsets now that, including Microsoft HoloLens 1 and 2, that sit kind of in the middle and allow you to interact both with physical and digital objects simultaneously. We want robots to sit here in the middle as well, because they exist obviously in the physical world, but they generate and interact with digital data. So whether it's their sensors or maps that they have of the space that they're operating in, they naturally interact with the digital world as well. And so we see robots as just another class of mixed reality device. And I'll talk about sort of the two most relevant classes of mixed reality devices, at least with respect to what we offer from Microsoft. So augmented reality on mobile devices. You can see digital content as an overlay on the real world and to some degree interact with it through the multi-touch interface on the mobile device. So in this case, you can see a little GIF from the Minecraft Earth game where you can have an augmented reality game board in your space and overlaid on your real world. There's a lot of AR content and apps that leverage AR Core and AR Kit, and also research in this direction using augmented reality and robots for colocalization. But often this gets done with fiducial markers, which is something Helen will talk about more later. The other key class of devices is immersive, is mixed reality headsets like HoloLens 2. This new device, relatively new now, offers the ability to not only visualize mixed reality holograms, but also interact with them using kind of fully articulated hand tracking and eye tracking, which I'll talk a little bit more about later. These different ways that the device is able to sense the user's means of interacting with the digital content. We can leverage these same things to interact with robots. And so really the HoloLens is kind of a moving sensor platform. So you have a number of different sensors on board packed into a very small form factor. You have 4 head tracking cameras that track how the device moves through the environment. You also have a depth camera that has 2 different modes. One, short throw, helps for tracking your hands. The long throw mode helps to map the environment. And you also have some small IR cameras that track the eyes, as well as microphone array and another RGB camera. So there are a lot of sensors on board. All of these sensor streams are potentially useful in interacting with robots. But what's interesting is that many of the same operations that the HoloLens is doing as far as tracking how it moves and understanding its environment are exactly the same problems that a robot needs to solve in order to understand its environment and operate there. So to give a sense of what HoloLens 2 does with these sensors, the head tracking cameras track a bunch of features in the environment and perform highly accurate visual inertial odometry along with the IMU. And this algorithm is highly optimized for power. So over long trajectories can track how you're moving your head. And simultaneously, you have the depth camera sensing the environment, alternating between the short throw and long throw modes in order to both track the user's hands and map the environment. And so all of this depth data gets fused into a spatial mesh of the environment. And this allows the HoloLens to project holograms in the right place so that they're not, say, behind a wall, and also be able to understand some semantic aspects of the environment, such as which parts of the mesh are walls and what is floor, what are other surfaces that you could put holograms on. And so with all of these different processes running simultaneously, the HoloLens is able to build up a very rich spatial representation of the environment, which is very useful for visualizing digital content for the user. But it also allows the HoloLens to have a rich understanding of the environment that it can share with other agents such as robots. And among the ways that the HoloLens can allow the user to interact with digital content is with this fully articulated hand tracking, in which the user is able to really just reach out and touch holographic content and manipulate it, which makes for a really intuitive interaction with these digital objects. And we can leverage that also in interacting with robots. And the way this looks is like this. And so you really do get tracking data for all of the parts of the hand, and it's really quite robust. And what's interesting is that this was actually trained purely on synthetic data, and is able to really adapt well to a wide variety of users and background environments. Finally, the eye tracking capabilities allow you to use your gaze to direct either to control holograms, and also obviously we are interested in trying to leverage this mode of interaction for robots as well. So VR headsets, on the other hand, really only allow an occluded view of the environment. You can only visualize digital reality. There is one exception to this, which is called Pass-Through Plus for some Oculus headsets, which allow you to they reproject the images that the cameras on the device that help to track how it moves. They reproject those to the displays on the inside of the device, so you can kind of see through to the outside, albeit with a limited field of view. But that's one exception. I don't know of any work in that area for doing kind of MR control of robots, but that's maybe a possibility. And there's also some functionality for VR headsets to do hand tracking rather than using controllers, which are pretty typical. And there's a few other sort of a few other types of ways that we can mix the real world and the digital world. So one of them is the mixed reality capture. There's a studio that's part of Microsoft that allows you to do like high resolution volumetric capture with a lot of cameras that allow you to basically generate really nice looking holographic content from real world from real people or objects, and then you can visualize these through an MR device as a hologram. Another sort of another way of visualizing real world and digital data together is with what's called Oculus mixed reality capture that allows you to visualize yourself into the game content. As far as I know, neither of these have been explored for interaction with robots, but as you can see with all the different types of devices and different ways of blending the real world and the digital world, there are a lot of opportunities still to explore for leveraging the physical and digital worlds for robotic use cases. So now that we've talked about devices, we can discuss a little bit about how about the development ecosystem for building applications that leverage mixed reality for robots. So the biggest thing is communication. So being able to communicate between devices is typically a challenge, and this is a challenge whether you have mixed reality devices at all, even just between robots. It's also, one of the most central aspects of a robot system, especially a distributed one across many different robot devices, is how are you going to send data back and forth? On mobile devices, you have the option to use a package called ROS Sharp with a ROS bridge that facilitates communication. There's a few other options for Android and iOS. ROS here stands for Robot Operating System, which is not an operating system, but a communications framework that is popular in both the research and commercial domains for mobile robots. And the ROS Sharp package enables this to work with C# projects. And luckily, that also works for HoloLens and UWP applications. There are a few other options also for HoloLens, but because both of these use cases are supported by ROS Sharp and ROS Bridge, this seems to be, for now, the best way forward for communicating between your mixed reality device and your robot. There's a number of development platforms that enable the user to create 3D content and build spatial applications that can then interface with a robotic agent. Unity and Unreal are both game engines that have found a lot of use in more general 3D computing. And there's also the OpenXR standard, which is looking to sort of make mixed reality content available to a wider variety of devices through standardization. There's also the WebXR, which is a JavaScript library that allows you to have 3D content on the web. And sort of building on the sort of the basic development platforms, you have a few options for getting components into your mixed reality applications that allow you to easily build interaction and interfaces for user experiences. So one of them is PTC Vuforia, which is a framework mostly targeted at enterprise applications for building AR and MR applications across different platforms. There's also Microsoft's Mixed Reality Toolkit, which is available for both Unity and Unreal Engine. That, if you look in the bottom left here, gives you a bunch of different components for adapting to your application that allow you to interact in different ways, whether it's through hand manipulation or eye gaze or different ways that you can easily interact. These pre-built holograms will allow you to easily get the user's input for the user experience. This is also compatible with ROS, the Robot Operating System, which makes it a compelling tool for integrating into a robotics project in this space. And finally, there's a project called ARViz, which adapts the RViz visualization utility from ROS for mixed reality devices. So what kind of data is useful to visualize? As I mentioned before, robots typically have a bunch of sensors on them. And while it's possible to visualize all of this data, you see from a few of these examples that if you look at, if you try to visualize a mesh or the robot's raw sensor data, you might end up occluding half of your field of view with opaque holograms. And so that's something at least to consider in building a user experience in MR that deals with robot data is what kind of data provides the most information to the user and also doesn't interfere with their ability to view the real world that they might also be trying to interact with. So good ideas for this include paths or the frustum of the camera, what it's looking at, the current robot state, or reference frames for the robot's map origin or its goal location. And another thing to consider when working with spatial data is that you're typically going to be dealing with many different reference frames. So in order to share spatial information between mixed reality devices and robots, you'll first need to co-localize your two devices. That'll be the focus of the second half of this presentation. But you'll also have to deal with handedness of your coordinate systems. So for example, Unity is left-handed, ROS and others use right-handed coordinates. You also need to deal with different orientation conventions. So HoloLens uses Y up while ROS uses Z up, and so on. These are all small details, but important to keep in mind. There are many different ways to represent spatial information. And to make this easier on yourself, if you are using ROS, it's a good idea to leverage TF, the package for handling transforms, which will do this for you, most of this. And there's also some functionality built into ROS Sharp to handle the conversions between left-handed and right-handed for between Unity and ROS. So a lot of this can be taken care of with careful use of the existing tools. So different modes of interaction. If you're working in the physical reality, your possible ways of interacting with robots, typically with joysticks or controllers, as you can see on the left, and also kind of traditional keyboard and mouse, where you interface with the robot using some visualization program. In augmented reality, it ends up looking like this, where you can use buttons or click on parts of the screen to indicate position in space. If your augmented reality device is localized to the same space as your robot, then you can visualize spatial data from the robot overlaid on your view of the real world through the AR device, which you can see here. The position of the robot is this blue sphere, path is these red dots, goal is this white and green marker. And in mixed reality, you have some more options for actually interacting with the digital content. Instead of through a screen in AR, you can actually use your head pose, your eye gaze. You can touch or move holograms, and you can also point to distant ones with your hands. And so this offers kind of a more rich palette of modes of interaction for communicating with robots. Finally, in virtual reality, you have also head pose, but typically your way of interacting with any of the digital content is with controllers, which do have some advantages for manipulation, because you can somewhat easier interact with distant digital content, and you have a bunch of buttons for other functionality. So there are some advantages to using controllers rather than your hands, but it's maybe a little bit less natural. So some final considerations when you're developing a mixed reality application for working with robots. Your basic system architecture might just be your mixed reality device communicating with your robot. But you might also, because of limited computational power on your HoloLens and your robot, you might have some things running on your on a base station or laptop computer nearby that's on the same network. You might even, if you're working with a complex application, you might be using some cloud services that need to interface with all of these devices. So your communication might become somewhat challenging over time as the complexity of your application grows. So this is something else to consider in designing your system, and whether you want to depend on communication with like a persistent link to the internet or not in the capabilities you can provide. So to briefly summarize this first half of the webinar about interaction, goal that we see for interaction is to enable human-robot teamwork. And there are currently many devices available that enable some capabilities in this direction across the mixed reality spectrum. And these different types of devices, depending on their capabilities, offer different modes of interaction and visualization of robot data. And all of this really depends on being able to have a shared spatial understanding of the world between the mixed reality device and the robot. And that is the topic of the second half of this webinar. So now I'm going to hand it over to my colleague Helen, who will take over for the second half.
Thanks for the introduction, Jeff. I'm Helen Oleynikova, a senior scientist at the Mixed Reality and AI Lab in Zurich, same as Jeff, and I'll be talking about how to co-localize robots and mixed reality devices. There's a few different types of co-localization that we need to talk about. The first type is when a person knows where the robot is relative to them, so the relative localization between the device and robot is known. So for example, the person can see the robot's state and intentions, it can see any path that's been planned. And the second type is where the robot knows where a person is. So this can be used for example, avoiding the human in robot path planning, and can lead to a much more natural interaction experience, as in the Come Here demo. And finally, the most rich of the types of colocalization is when the robot and the person are both localized in the same global coordinate system, and they can share information that they both have about the space. So we'll discuss a couple of different methods of colocalization. So the first and possibly most commonly used is marker-based. So this includes a wide variety of AR markers such as April Tag, Aruco, AR Toolkit, ViewMark, and so on and so forth, similar to the ones you see on the right here. Then there's also vision-based approaches. So these basically use visual information, so image features and so on in the environment, to provide localization information. So this includes Azure Spatial Anchors, which we'll discuss in some detail, Google Cloud Anchors, Apple Location Anchors, and so on, and quite a lot of different methods in research. And finally, we'll briefly talk about common maps. So this is using different localization schemes or different sensors between the two devices to find a common coordinate system by localizing themselves in a common map. So first, we'll discuss a little bit about marker-based colocalization, how it works, advantages and disadvantages. So how do localization markers work? So here you see a picture of a group of robots, each with markers mounted on them. So basically, the algorithms work by detecting this quite distinctive black and white pattern in a camera image. And what's really powerful about the markers is you can actually differentiate different marker IDs. So each of these robots has a different marker ID, which is shown in a different pattern. And this means that by just looking at this image, you're able to get all of the poses of all of the robots relative to the camera frame. So that's quite powerful. And there's a couple of different ways to use them. So one way is to have all of the devices use their onboard cameras. So here we have a HoloLens 2, a mobile phone, and a robot. All of the devices use their cameras to find where the marker is mounted statically in a scene. And then from that information, by using the shared coordinate system, they're able to localize themselves with respect to the marker, and by sharing the data where all three of them are relative to the marker, they can localize each other. Another potential system is similar to what we saw in the previous photo with the multiple robots, is to actually have the tag on the object you want localized relative to yourself. So here the HoloLens and the phone are both detecting a marker that's actually mounted on the robot, and by calibrating the marker pose to the robot's base link frame or some static part of the robot, then you're able to get a full transformation between the cameras of the sensors and the robot. Keep in mind this gets a little bit more complicated if the robot is moving and with latency and network delay, so you'll have to this method is a little bit more complicated in that regard. So what are the pros and cons? So again, markers are super commonly used for a wide variety of AR and MR applications. So they give you very precise positioning. So on average, and this depends on a huge variety of factors, including camera resolution, the quality of the calibration, how well the marker is printed, how far away you see it from, what angle you see it from, and so on. But under good conditions, you can get sub-centimeter and sub-degree accuracy under such conditions. It's fairly fast, so if you decimate the image down and so on, kind of an average performance is about 22 milliseconds per image on a slowish computer. So it's fast enough to run on mobile devices and onboard robots. So again, quite good there. It's cheap and easy, widely supported, many varieties. You can pick any flavor of AR tag and get kind of similar performance. The big downside is you need to actually do something to your environment or to the robot to be able to use this. So you can't just show up in a new space where you haven't done anything with a new robot and be able to use it. You need to go around taping tags. You have to make sure no one takes them off at night or moves them. Or on the robot, again, you have to make sure that the tag is rigid with respect to the robot. And so basically all the agents you want to interact have to be looking at the same tag or series of tags, and then you can do quite complex multi-tag setups where you basically create a sparse graph of tag locations relative to one another. But this, again, this gets quite complex. If one of the tags moves, what does this mean for the map? If you observe 5 tags and one of them is out of place, what does this mean for your map, and so on and so forth. So this quickly grows in complexity for the problem. But for quite simple scenarios, this is often a great solution and really fast and easy to implement. And of course, the accuracy is viewpoint dependent. So if you're, seeing a tag on a really weird thin angle, you're going to have much worse accuracy than if you're looking at it head on. So a little bit of detail about how one of the AR tags works, just so you get a sense for the general algorithms and pipelines that it takes to do this. So here we'll use the example of April Tag 2, which is a paper by John Wang and Edwin Olson. Please check out their paper for more technical details and many more cool figures. So here we see the original image, which is taken with a normal color camera. This could be from a phone, from a robot, whatever. Then the next step is to do edge detection. So here you can see the edges in black and white. This is just done by adaptive thresholding on the edges. Then all of the edges are clustered into connected components. So basically all of the edge groups that are touching each other are separated. And then in these clustered components, they detect quads, so rectangles, squares, and other quadrilaterals. So these are kind of the candidates for the outer shape. And then after the correct size markers are found, then they kind of extract the contents of the quads, they unwarp it, and then from that they're able to get the actual IDs of the tags, which are what's overlaid here. So again, fairly simple system, but you can run this quite quickly. You can do GPU acceleration on this and so on. So it's quite flexible and fairly robust in the presence of, for instance, camera distortion and other effects. So how does this work in practice? So here we see a video from Robotics on how they're using AR tags to actually dock their robot. So this is kind of a mock-up of how they would do wireless charging for docking. So the robot is able to just kind of spin around in the space and then very accurately come home by just using a camera and its relative position to this tag. So again, if you imagine you had a wireless charger here, you have a complete wireless charging solution. And of course, you can also use this directly with augmented reality. Here it's actually a QR code, and here they're rendering on top of the QR code a robot arm, which you can control from Unity. This is done with Vuforia. And so you can see when the person actually picks up the QR code, because it's so fast to detect these types of markers, the robot moves live. And you're able to very easily interact with these markers and manipulate them. And this is, again, not work from us. This is work for the Brno University of Technology. So next up, we'll talk about an alternative if you can't instrument in the environment, or for some reason you don't want to, or you want to use the information about the environment for other applications, and that's vision-based colocalization. So there's kind of a standard pipeline that's very frequently used in computer vision and robotics. So here we take some work from Bernard Zeisel and his work with Mark Poleface on using photographs to build and augment 3D models. So again, not our figures. So the first step is to basically extract features from an image by kind of finding corners and kind of distinctive locations in the image and getting their description. And then assuming you already have built a 3D model, you can add a new query image in there. You can extract local features there as well. Then to compare to the 3D model you have of the space, you can do 2D to 3D correspondences through descriptor matching. So this means kind of taking the local patch around the image features and then comparing it to local patches around image features in the pre-built map. Then from having enough of these correspondences, you can basically figure out what the 6th degree of freedom poses, and then you get the final camera pose in the map. And the original map is created in kind of the same method. You just do this frame to frame. So in consecutive camera frames, you would do this feature matching, and then triangulate 3D key points, and then be able to create a similar map to what you see here. So of course, this is not an easy problem, which is why a lot of people have been published a lot of papers about it. So there's quite a few issues. So here you can see a 3D map and examples of what a single key point might look like over different lighting conditions and over time. So as you can see, we're trying to focus in on this exact point here, and it looks very different over different seasons from different perspectives under different camera parameters and at different times of day. So it's quite hard to do this kind of descriptor matching over time. So how can we use this kind of visual pipeline to localize a robot? So here you see a work from the Autonomous Systems Lab at ETH Zurich, done with Google Tango tablets. So here they're demonstrating basically an inspection trajectory for a robot to fly. So by walking around with a tablet, they're recording this sparse visual map, which you see in yellow here, and indicating points of interest that the robot should inspect. So then by sending basically this 3D map with visual features to the robot is able to localize itself to the map, which is step one, and then be able to repeat this demonstrated trajectory and inspect all of the points of interest at hand. So even though the tablet and the robot have very different sensors, they are obviously quite a bit different, they're able to use the same visual features to relocalize. Okay, that's great. There's a lot of research on this. How can you use this? So luckily, there's also a lot of cloud services that offer this exact functionality for augmented reality and mixed reality applications. They include Azure Spatial Anchors, which we'll talk about a little bit more in a second, Google Cloud Anchors, and Apple Location Anchors. So basically, no matter what platform you're using, there's at least some kind of vision-based localization system for you. So, most of these systems work in a very similar way. So basically, you're able to place anchors, which represent a common reference frame for attaching holograms to, replacing digital content, or just having some persistent coordinate frame in the world. And their goal is to keep it stable to the real world. So using AR or MR, you physically place some anchor that you want to stay the same. And by using kind of the visual features in the environment near the anchor, all of these systems use a very similar method to what I just described to create a 3D visual map and enable you to relocalize back to this anchor coordinate frame over time. So again, the most important part of this is that it should be persistent over time, and all of these use the cloud. Some of these are optionally usable kind of on premises or on device. And you're able to attach cute dogs to your anchors. And here's an example of, so for Azure Spatial Anchors, what this looks like in the background. So this is an example of a scene, and here's what the visual map looks like. And as you can see, it's just a collection of 3D points. And just looking at this map, you probably wouldn't be able to really figure out what's what. Maybe this is this shape here. That's possibly the edge of the chair. But the important thing is each of these 3D points actually contains a description of the local neighborhood. So here, for example, on the edge of the chair, you would have this black to white transition and the kind of general local shape of the chair described. So you're able to, even if you view it from a slightly different angle at a slightly different time of day, you'll be able to re-recognize that again. So here's kind of a video that shows how this works. So here we're creating a spatial anchors. And then by kind of scanning the space and getting enough data, the anchor is created. And now we're able to, on multiple devices, by both localizing to the same anchor, we're able to share the space and, share the same view of a 3D model. So again, this is just a way to anchor digital information to the physical world. How does the system work? So we'll talk a little bit about specifically Azure Spatial Anchors and how you can use it in your work. So at release, Azure Spatial Anchors worked with ARCore and ARKit enabled devices, so iPhone or Android phones, which took the images and poses from the AR framework. Also with HoloLens 1 and 2, which takes basically in that case directly image features and poses from the head tracking. And most recently, we've introduced the Azure Spatial Anchors Linux SDK, which is a research distribution which allows you to kind of bring your own simultaneous localization and mapping framework. So you can get your poses from wherever you like. All you need to do is put in the undistorted images and the poses of the camera when those images were taken, and you're able to utilize this framework. This is all done within a session. So a session contains kind of the image features and image poses in a short span of time. And from that, you can create anchors by specifying a relative pose relative to the current device position and get a unique anchor ID in return. And then other devices or yourself again can query the same anchor ID and get the relative pose in return. So you can create anchors on any of the devices and query them again on any of the devices shown here, which makes it quite a powerful system. The only restriction is you have to be connected to Azure. This is a cloud-based service and cloud-based service only. So let's take a look at how this works on the real robot. So here's we see a HoloLens localizing to a spatial anchor. This is the onboard HoloLens view. You can saw the coordinate system just pop in. Spot is able to localize to the same anchor by using the image data from one of its front-facing cameras. Once both the HoloLens and the Spot have found the same anchor, they know each other's pose and their pose relative to one another. This allows great human-robot interaction scenarios. For example, sending Spot to a goal from the HoloLens point of view and the come here gesture we showed at the beginning of this presentation. So last of all, we'll talk about the scenario where you actually don't have vision-based sensors, so cameras, on all of your devices. What if you have a robot that's navigating the world using only LiDAR? Can you still interact with it using a mixed reality device? How do you bring both into the same coordinate system? We'll show a demo we've done of co-localizing a ClearPath Jackal, which is using a 3D LiDAR as its main sensor, together with a HoloLens, doing kind of the same demo we've shown with Spot. To do this, we first create a full 3D map of the environment using the HoloLens. So the HoloLens has a depth sensor on board, as Jeff discussed, and we use that to reconstruct a full 3D mesh of the environment. We then upload this to a server and then extract a 2D LiDAR occupancy map for the robot to localize against. So we need to give it kind of a rough guess of its pose. And basically now the HoloLens is localized against a spatial anchor that's at the origin of the map frame, and the robot is localized against its 2D LiDAR map, which you can see here. This allows them to share the same coordinate system, even though they use very different sensors. And this allows kind of the same human-robot interaction scenarios we've discussed before. And here you see a top view of the 2D LiDAR map that the robot is using, some obstacles overlaid on top of it, and the live sensor data. So in summary, we think colocalization is crucial for human-robot interaction with mixed reality. And there's quite a few different ways to do it. So probably the simplest and easiest is markers. So instrumenting your environment with some kind of AR markers. Then you can do much more complex scenarios in unstructured environments using vision-based localization. And we discussed Azure Spatial Anchors Linux SDK that allows you to co-localize your robot with MR devices directly. And finally, there is an approach to do this through a common map, which we built on the HoloLens. And in conclusion for the whole talk, we hope that you've learned from this that robotics and mixed reality are a natural fit. So mixed reality can give you insight into robot state and plans, more natural interaction models, and also get information that actually the robot can use for increased autonomy. We've also talked about many tools available to solve fundamental colocalization problems, including vision-based, marker-based, and map-based. And we're really excited to be a part of a new and growing field of mixed reality robot interaction. And we hope you've kind of learned the tools to get started here too. Finally, we want to thank everyone for attending. Thank you so much for your patience. We really hope you enjoyed the talk and learned a lot. Please stay tuned for the Q&A. And I'd also like to give a special shout out to our amazing interns who really heavily contributed to what we've shown today, who are Oswaldo Ferro and Eric Vollenweider.
Hello, everyone. Thanks for attending our webinar today on mixed reality and robotics. My name is Jeff Delmerico. I'm here with my colleague Helen Oleynikova. We're going to start the live Q&A right now, and for the next 15 minutes or so, we'll try to answer some of the top questions that you've submitted during the webinar, but please feel free to submit more questions if you have any particular topics you'd like to know more about from the webinar, or more generally about mixed reality and robotics if there are things we didn't talk about. I think I'll start off with the question that came to us. So how much do you lose in accuracy and performance with vision-based localization versus AR tags and markers? And what kind of settings can vision-based localization be reliably applied to? So I think this fits into a more general topic of sort of what are the limitations of different localization technologies. And so in many applications, at least in terms of user experience for AR and MR experiences, it's often the localization accuracy. The really key piece is how it looks to the user. And so if for example, your Minecraft Earth board is supposed to be on top of your table and it's 3 meters away floating in midair, that's not a very good experience for the user in terms of localizing to the visual features on your table. But on the other hand, if it's only off by 15 or 20 centimeters, then it might look fine. And so that's sort of the requirements for human experiences are somewhat different than for robotic localization, where if your robot is off by 20 centimeters, it might bump into a door. So currently, the technology we have for Azure Spatial Anchors is accurate and reliable enough to provide good user experiences. And as we look to the future, we're also interested in trying to make these the vision-based localization also work for the levels of accuracy that we need for robotic tasks. Maybe, Helen, I'll hand it over to you for the next question.
Yeah, so the next question we wanted to talk about, which we thought was interesting, was how do you see the roles of humans and robots in a human-robot collaboration? And I mean, this is much more about kind of our vision for the future. And as we discussed in the presentation, there's like robots are becoming increasingly more useful, but where they're currently most used commercially, or at least what we consider autonomous robots, is really just moving things from point A to point B, and logistic robots and in warehouses where everything is flat, everything is pre-mapped, and the environment is somewhat known and stationary. And I think really the next step, it's not necessarily that we're going to get incredible autonomous robots that can do everything on their own and solve every problem and do things that humans can't even imagine doing. I think we're really a long way off from that, just because these problems are very difficult to solve. I think what really is going to push robotics forward a lot and making robots much more useful is to enable humans to do some of the decision making, to have humans and robots work together side by side, because some tasks that might be super simple for a human, for instance, identifying cups or figuring out how to pick something up or figuring out the right way to turn a part around for some operation, this is super easy for a human and can be really difficult for a robot. Whereas, lifting 3 tons could be very difficult for a human and super easy for a robot. So I think there's really a lot of many opportunities in this field for, allowing humans to really use the knowledge and do the things that are very difficult to do autonomously, and kind of do the leave the more mechanical work and things that are much simpler for robots to do to robots. So I think it's going to be a very long time before robots can really replace humans in most spaces, but hopefully they can take away, some of the dull, dirty, and dangerous tasks, or at least help humans complete them in a safer, more efficient, and faster way. And I'll hand it back to Jeff for next question.
Thanks. I'll take the next one, and this is actually a couple of related questions about the Azure Spatial Anchor service. So the question was, are there any on-premises solutions available for ASA, and do you plan to provide them, or are there other solutions, kind of enterprise solutions, to provide similar functionality? And so that's a good question, because currently the way that Azure Spatial Anchors works, you have to send data to the cloud. So you need to have a persistent internet connection, whether it's from a mobile device or HoloLens, or now in this case from your robot. And the map is stored in the cloud. You don't download the map. You don't have that locally. You can't redirect your query to a local server. That all has to be done in the cloud. Obviously, that's a problem for many robot scenarios. If you think of just like a large warehouse or factory, you might not have good wireless connectivity throughout the space, or it might be expensive to provide that. And in a lot of the other types of scenarios where you want to send robots to do dangerous jobs, for example, there might not be any connectivity at all. And so we certainly see the need to relax this requirement. And the other dimension to this is that often for enterprise customers, you don't necessarily want to put your maps of your space in the cloud, even if it's not possible for other users to retrieve that information directly. There's certainly cases where users would need to have their map data in a more secure way. And so certainly our ambition is to be able to provide the mapping technology to to enable these sorts of scenarios where it's possible to leverage the cloud when that makes sense, and when it's also possible to have on-premises maps that can be queried through a local server for customers that don't want to share their data in the cloud or can't send queries that way. And also, there's definitely a limitation on the scale that we can support right now. Individual spatial anchors are relatively small scale, and when placing them in a single session, they can be, connected together, and that's nice for still kind of, let's say, office scale environments. But the ambition is to be able to map, large, as another question asked, city street level, city blocks, large venues, factories and warehouses, things like that. So, we're very interested in that. Our group here in Zurich works on some of the mapping technology that is, geared towards future-looking things like this. And so we're very interested in being able to provide that in the future. Maybe I'll hand this over to Helen now.
Yes, I'm looking for more questions that would be interesting to answer. I think we've actually done a pretty, well, we've been trying to kind of answer most of these as we go along in the chat. Let me read some of the newer ones. Okay, so I quite like this one. So the question is, one of the discussions suggested that colocalization could be used to consider human as an agent to enhance safety alongside robots. Given the reliability on cloud, can it be trusted for safety of humans, or is there a backup that you're working on? So for sure, relying on cloud-based localization as a single degree of safety that's certainly not safe enough. But I think there's applications in especially industrial environments where you have much more control over kind of what the workers are doing and so on. That you can be, for instance, required to wear some kind of mixed reality device or some kind of localization device while performing some sort of task. And in these cases, in addition to more standard industrial safety measures, then the robot having more insight about where a human might be or might not be, it's just it's another source of information. Maybe you have kind of earlier warnings that a person is approaching than you would just from laser-based safety systems. So I think I fully 100% agree that this is like not nearly safe enough as a single layer, but I think there's environments where, in addition to many other fail-safes, it can actually be quite useful. So I'll hand this back over to Jeff.
Yeah, I just reading the couple more questions that we've received, and we have another minute or two, so we'll probably just take this as the last question for now. And this question: do you observe much drift with colocalization between HoloLens and robot? This is actually, this hints at a broader class of sort of challenges for doing cross-device localization. So if you're mapping your space with visual features, right? So you're calculating features in images that you see in the cameras on one device, let's say a HoloLens. then it's on your head, and particularly if you're a very tall person, but even if you're a normal-sized human, you're quite a bit taller than most robots, which are going to be moving along the floor, and their cameras are also along the floor. So the things that you see in the camera images on the HoloLens that's on your head are going to have a very different perspective than what you can see in the camera images on a robot that's walking along the ground. And separate from just the perspective, if you're looking down on a table or even just on the floor, even if there's no occlusions, the way that you can see features and how those appear to your device will look different than to the robot. And that's not even considering differences in focal length and field of view and resolution. There's a lot of challenging research questions for kind of cross-device place recognition that are independent of even just the fact that you're taller than your robot. But that's definitely an issue. It's with the Azure Spatial Anchor service, if you place anchors with one device and you try to recall them with another device, your performance, your accuracy is going to be noticeably different. Often it's still sufficient to support the kind of AR experiences that we want to provide through having these spatial anchors, but often the accuracy is degraded quite a bit compared to recalling the anchor on the same device or the same type of device. And so this is definitely something we need to consider as we, if we build maps from the robot that we want the human to use with mobile or head-mounted devices, or if we make maps with human devices and we want the robot to localize to them. There is a challenge there to achieve the same performance as when the devices are the same. And I think we're pretty much out of time, Helen, unless you have any high priority final questions here that just came in that you want to answer.
I think I'm all good from my side.
Okay. Yeah, so I just want to thank all of you for attending today, for submitting lots of really great questions. Really appreciate your interest in the subject, and I think somewhere within your view, there's a resource list on the right that has some links. We've done there should be hopefully a few things of interest for you there, a recent blog post, and some links to GitHub with code samples. And I'd also like to call your attention to the poll. I'm not sure where that is in your view, but if you can take a moment to answer, I think there's only 4 questions, just to help us get a better understanding of the audience here, that will inform our kind of future communications as well. And certainly, thank you for taking the time, and thanks for your interest, and do reach out to us if in the future if you have further questions and so on. Great. Thanks so much. Have a great day.